Welcome to Induced EMF. This is Review Lecture 7.1a, Part 1 of 2 parts. Upon finishing this, you should be able to determine the induced EMF and current, determine the direction of the induced EMF and current, use Faraday's and Lenz's law, and determine magnetic flux. Okay, so in 1831, two physicists, Michael Faraday in England and Joseph Henry in the United States, independently discovered that magnetism could produce an electric current in a wire. Their discovery was to change the world by making electricity so commonplace that it would power industries by day and light up cities by night. And also, those cool shaker flashlights and crank-powered emergency radios, we owe those to these two people here. No battery or other voltage source was needed to produce a current, only the motion of a magnet in a coil or wire loop. A voltage or EMF was induced by the relative motion of a wire with respect to a magnetic field. So the production of EMF depends only on the relative motion of the conductor with respect to the magnetic field. EMF is induced whether the magnetic field moves past a conductor or the conductor moves through a magnetic field. The results are the same for the same relative motion, magnetic field, and conductor configuration. The amount of EMF induced depends on how quickly the magnetic field lines are traversed by the wire. Very slow motion produces hardly any EMF at all. A quick motion produces a greater EMF. Increasing the number of loops of wire that move in a magnetic field increases the induced EMF and the current in the wire. Pushing a magnet in twice as many loops will induce twice as much EMF. So for instance, here this might produce 1 volt of EMF. This is twice as many loops. That would produce 2 volts, and this is 3 times. That would make 3 times as much EMF. However, it would be much harder to do this than that. So the effort increases as the number of loops increases because you can't get something for nothing. We don't get energy for nothing by simply increasing the number of loops in a coil or wire. The work is done because the induced current in the loop creates a magnetic field that repels the approaching magnet. So if you try to push a magnet into a coil with more loops, it requires more work to do it. If you push it faster, it requires more work than if you push it slower. In fact, the coil produces a magnetic field of its own that opposes any change in the magnetic field of the coil. This is Lenz's law, which is the conservation of energy law. So in case here we have a coil or a loop and a bar magnet. When the north pole of the bar magnet is pushed toward the loop, a current is induced in the loop. The current produces a magnetic field, that's represented by this imaginary yellow bar magnet, with a north pole which repels the bar magnet's approaching north pole to try to keep it away. When the bar magnet is pulled away, on the other hand, the loop's induced current is in the opposite direction, producing a south pole in the loop. The loop's magnetic field south pole tracks the bar magnet's retreating north pole to try to keep it from leaving. Each time there's relative motion between the magnet and the loop that changes the magnetic field in the loop responds by producing its own magnetic field that opposes the change. That's Lenz's law. Note that the current reverses each time the relative motion reverses. This is alternating current, AC. Now, you don't need a magnet. You can use another loop because remember, a loop will create its own magnetic field. You just have to make the magnetic field change. So in other words, if we make the magnetic field from this loop change, it'll induce a opposing EMF in this second loop. And you can do that by just opening and closing the switch. Okay, so the law of energy conservation applies here. The force that you exert on the magnet multiplied by the distance that you move the magnet is your input work. This work is equal to the energy expended or possibly stored in the circuit to which the coil is connected or to heating the coil. You have to do work to produce a current in the coil. If the coil is connected to a resistor, more induced voltage in the coil means more current through the resistor. I equals V over R. This means more energy expenditure. P equals I squared R, or V squared divided by R. Inducing EMF or voltage by changing the magnetic field around a conductor is called electromagnetic induction. So these are all variations on a theme. An induced EMF appears in the loop whenever you change the magnetic field in it by doing any of the following. Moving a bar magnet toward or away from the loop. Moving the loop relative to the bar magnet. Moving a current-carrying coil relative to the loop. Moving the loop relative to a current-carrying coil. Changing the current in a current-carrying coil. Rotating the loop, changing the number of magnetic field lines that passes through it. Changing the area of the loop to enclose a different number of magnetic field lines. In short, anything which changes the number of magnetic field lines passing through the loop, or alternately, anything which changes the magnetic flux through the loop, will induce an EMF in the loop. Now, this is Physics 222 calculus based. If you are Physics 122 algebra based, please skip to slide 11, which is one slide down. Okay, so magnetic flux, Physics 222. Now, if you remember electric flux, it's pretty much the same thing. The only thing we got different here is now we're talking about magnetic flux instead of electric flux. So we have an area here, and we have a magnetic field instead of the electric field that is the area. And it happens to do so at an angle theta with respect to the normal. Remember, we always measure angles relative to the normal. The magnetic flux phi b through an area A and a magnetic field B is defined as phi b equals the integral of b dot dA. Units on this are the Weber. The Weber is a Tesla meter squared. The integral is taken over the entire area. Okay, so if the magnetic field is uniform over the area, phi b is just BA cosine theta, or B perpendicular A. If B is perpendicular to the area and uniform over it, the flux is phi b equals BA. If you are a Physics 222 student, please skip ahead to slide number 12. If you are a Physics 122 student, which is algebra based, you belong here. Okay, we have an area here, and we have a magnetic field that pierces the area at an angle theta with respect to the normal. Remember, we always measure angles relative to the normal. The magnetic flux phi b through an area A and a magnetic field B is defined as phi b is approximately equal to the sum of B delta A cosine theta, where delta A is all these little areas. The units on that is the Weber, and a Weber is a Tesla meter squared. And the sum is taken over the area. Now, if this sounds familiar, remember electric flux? Yeah, it's the same thing. The only thing different is we're talking about magnetic field instead of electric field, and we're talking about magnetic flux instead of electric flux. If the magnetic field is uniform over the area, phi b is just BA cosine theta, where theta is this angle between the normal and B. Or we can rewrite that as B perpendicular A. If B is perpendicular to the area and uniform over it, then the flux is phi b equals BA. Okay, now Faraday's law and Lenz's law. Faraday realized that an EMF can be induced in any loop, even a non-conducting loop, by changing the amount of magnetic field passing through the loop. If the loop is a conductor, the EMF also induces a current in the loop. He further realized the amount of magnetic field can be visualized in terms of the number of magnetic field lines passing through the loop. He formulated Faraday's law. The induced EMF in a loop is proportional to the time rate of change of the magnetic flux through the loop. With the notion of magnetic flux, we can restate Faraday's law to a more quantitative and hopefully useful way. The EMF is minus d phi b dt, or for a coil of N loops, the EMF is minus n times d phi b dt. Now, this is for Physics 222 students. That's calculus based. If you are algebra based, we can rewrite this as the EMF is approximately equal to minus the time rate of change of the magnetic flux. So delta phi b delta t, or for a coil of N loops, E is approximately equal to minus n delta phi b delta t. Okay, this induced EMF always tends to oppose the flux change, and that's the reason we have the negative sign. That is Lenz's law, and it has to be there because of conservation of energy. Otherwise, you could get something for nothing. Now, how to change the magnetic flux to a coil? You can change the magnitude of the magnetic field to the coil. In other words, you put more magnetic field lines in here. We change the area of the coil or the portion of the area that lies within the magnetic field. You drag it outside here, or you change the area by pulling it apart or squeezing it together. We can also change the angle between the coil's normal and the direction of the magnetic field. Any of these would induce an EMF in the coil and a current if the coil is a conductor in the coil. And notice this one, if you keep turning this is an AC generator, this one right here. Okay, so now we're going to give an example. The induced EMF in a coil due to a solenoid. This long solenoid S, shown in this cross-section, has 220 turns per centimeter, carries a current I of 1.5 amps. Its diameter, big D, is 3.2 centimeters. In the center, we place a smaller 130-turn, closely packed coil C of diameter little d equals 2.1 centimeters. The current of the solenoid is reduced to zero at a steady rate in 25 milliseconds. What is the magnitude of the EMF that is induced in coil C while the current of the solenoid is changing? Now, the physics of this is a Faraday's law problem, magnetic flux. If you are a Physics 222 student, calculus based, you should be right here. If you are a Physics 122 student, algebra based, please skip ahead to slide number 19. It's the same problem. Don't worry about it. Okay, so back to Physics 222. the knowns, we write down the knowns. The number of turns per centimeter should be converted to turns per meter. Everything gets converted to SI. So little n is 22,000 turns per meter. The initial current is 1.5 amps. The final current is 0 amps. The diameter of big D is the diameter of the larger coil, or the largest solenoid is 0.032 meters. The number of turns is 130 turns. That's the smaller coil C. The diameter of that smaller coil is 0.021 meters. The time rate of the amount of check time that elapsed is 0.025 seconds, and we need to know the EMF. The formula for this is the EMF is minus N d phi b dt. Phi b, of course, is just B times A, and B is mu naught IN. This comes from the magnetic field for a coil, and this is just the definition of magnetic flux. The area of cross-sectional area is 1/4 pi d squared. Okay, we start putting this together. The EMF is minus N d phi b dt, or minus N phi b final minus phi b initial divided by dt over time. So then we end up with minus A and BF minus B naught over dt. And we can pull the area is minus 1/4 pi d squared. And we can rewrite B as mu naught Ni. So then it becomes, and then of course we play around with this a little bit more, and we wind up with the EMF as minus 1/4 pi d squared mu naught little n big N times this quantity, IF minus I naught divided by dt, or IF minus I naught dt. Okay, so then we say that the EMF, we start plugging numbers in now. The EMF is minus pi over 4 times 0.021 meters quantity squared, and that times mu naught, which is 4 pi times 10 to the minus 7 decimeter per amp, times our 22,000 turns per meter, times 130 turns, times the rate of current change, which is minus 1.5 amps, divided by 0.025 seconds. Okay, and it ends up being an EMF of 75 millivolts. Now, if you're a Physics 222 student, please go to slide 22. If you're an algebra-based Physics 122 student, please land right here. Okay, the knowns on this are 220 turns per centimeter. We convert that to SI. 22,000 turns per meter. The initial current is 1.5 amps. The final current is 0 amps. Diameter of the larger coil, convert to SI, 0.032 meters. The number of turns in that coil, the smaller coil, is 130 turns. The diameter of the smaller coil is 0.021 meters, and the time lapse in this is 0.025 seconds. You want to know the EMF. The formula for this is EMF is approximately equal to minus N delta phi B delta T. We know that phi B equals BA from the definition of flux. B equals mu naught IN for a solenoid, and A is 1/4 pi d squared from the formula for area. Okay, so we have an algebraic solution. The EMF is approximately equal to minus N delta phi B delta T, and we can plug in, and we end up with minus N phi BF minus phi B naught divided by the time that's elapsed. And phi is just A times B, so it's minus AN times BF minus B naught divided by the time elapsed. The area is just 1/4 pi d squared, and B is mu naught N times I. And if we reduce this a little bit more, the EMF is minus 1/4 pi d squared mu naught N, little n, times big N times the quantity IF minus I naught over delta T. At this point, we're ready to put numbers in. So we have minus pi over 4 times 0.021 meters squared times this is mu naught 4 pi times 10 to the minus 7 decimeter per amp times 22,000 turns per meter times 130 turns times the current change to minus 1.5 amp divided by 0.025 seconds. The EMF is 0.075 volts, or 75 millivolts. Okay, now Faraday's law of induction and Lenz's law. Lenz's law states an induced current has a direction such that the magnetic field due to this induced current opposes the change in the magnetic flux that induces the current. This induced EMF has the same direction as the induced current. Now, a lot of times, if it's a non-conductor, you actually won't get a current, but we always pretend we do get a current, and that way we use it to determine the direction of the induced EMF, because you always get an induced EMF, you don't always get an induced current. Now, in this case, we have a loop here. And as the north pole of the magnet is moved toward the loop, the magnetic flux in the loop is increasing. So an EMF and a current is induced in the conducting loop. The current will produce its own magnetic field with a magnetic dipole moment mu oriented upward. In other words, the magnetic dipole moment is basically the direction of this dipole's north field. So the north pole is up. to fight the increasing magnetic field in the loop. This is to oppose the motion of the magnet. Thus, the induced current must be counterclockwise as shown. You use the right-hand rule. You need your thumb up because your thumb points in the direction of the north pole of this induced magnetic field, or the magnetic moment, mu. So the thumb is up in the direction of the loop's induced field. Your fingers are curled in the direction of the loop's induced EMF and current, so around this way. Okay, which if you're looking at this from above, would be counterclockwise. If you're looking at this down from above. Okay, so some problem-solving tips. Decide whether the magnetic flux is increasing, decreasing, or unchanged. If it's unchanged, the answer is easy. No EMF is induced. No current is induced. If it is increasing or decreasing, the induced magnetic field due to the induced current points in the opposite direction the original field of the flux is increasing, because it always tries to fight you. In the same direction if it's decreasing, and of course at zero, the flux is not changing. Use the right-hand rule to determine the direction of the induced current. Thumb is in the direction of the induced field. The curled fingers are in the direction of the induced current and EMF. Remember that the external field and the field due to the induced current are different. The change in the external field induces the induced EMF and the current to fight the change. Remember that Lenz's law always fights any change in magnetic flux in a loop. So here are some examples because people have a lot of trouble with this. It's even hard to say. So we're pulling a round loop to the right, and originally the magnetic field, it was in a magnetic field, was just directed at you out of the page, and we're pulling it out of the magnetic field. So the magnetic field is pointing out of the page, and the field inside the loop is decreasing as the loop is pulled out. The loop will then develop a magnetic field to oppose this decrease. So the loop's induced magnetic field also points out of the page because it doesn't want the magnetic field to disappear. The right-hand rule, the thumb is out of the page, the fingers are curling counterclockwise. So the induced current and the EMF are counterclockwise. There may not be an induced current, but the EMF is still counterclockwise. Now, we are shrinking a loop in a magnetic field that is pointing into the page, and we're going to determine the direction of the induced EMF. The B field is pointing into the page, and the field inside the loop is decreasing as the loop is shrunk. The loop will develop a magnetic field to oppose this decrease. So loop's induced field also points into the page. So we take our right-hand rule, thumb into the page, the fingers curl clockwise around the loop. So the induced current, if any, and the induced EMF are clockwise. Now we have a loop here, and we have a south magnetic pole. It's moving up from below up toward the loop. So this south pole is approaching the loop from below. We want to determine the direction of the induced EMF. The B field is pointing into the page, and the field inside the loop is increasing as the magnet approaches. Why is the B field pointing into the page? Because it's pointing into the south pole. B field's pointing to the south pole of a bar magnet. The loop develops a magnetic field to oppose this increase. The loop's induced B field points out of the page. The right-hand rule says the thumb is out of the page, the fingers curl counterclockwise, so the induced current and the EMF are counterclockwise. Okay, now we have a current increasing near a loop. Determine the direction of the induced EMF. Use the right-hand rule for the current to determine the magnetic field from the wire is into the loop. So in other words, you grab the wire, okay, this wire right here, with your thumb in the direction of the current, and your fingers point into the loop right here. And the current is increased. The magnetic field is pointing into the page in the loop, and the field inside the loop is increasing as the wire's current increases. The loop will develop a magnetic field to oppose this increase. The loop's induced field points out of the page. The right-hand rule says the thumb is out of the page, the fingers curl counterclockwise, so the induced current and EMF are counterclockwise. Here we have I decreasing, and here's a loop. We're going to use the right-hand rule for the wire to determine the magnetic field from the wires into the loop. So you grab the wire with your thumb pointing in the direction of the current, your fingers point into the loop. So the magnetic field is pointing into the page inside the loop, and the B field inside the loop is decreasing as the wire's current decreases. The loop will develop a magnetic field to oppose this decrease. So the loop's induced magnetic field points into the page. Right-hand rule, thumb into the page, your fingers curl clockwise. The induced current and the induced EMF are clockwise. Now this one's a little hard to see. We have an electromagnet, okay, and it's connected to a battery and a switch. And when the switch is closed, the conventional current, you only worry about conventional current for these, The conventional current flows from the positive terminal of the battery around through the windings of the electromagnet. Now, the right-hand rule for the electromagnet, you wrap your fingers around the core of the electromagnet in the direction of the current. The thumb will then point to the left because your fingers are going over the magnet, over this electromagnet on top here. So your thumb is pointing toward the left. And that will be the direction of the magnetic field, and it's increasing. So the magnetic field is pointing to the left, and the field inside this small coil or loop here is increasing as the wire's current increases. The loop will develop a magnetic field to oppose this increase. So loop's induced magnetic field points to the right. Right-hand rule says thumb to the right, fingers curl out of the page at the top of the page, top of the loop, and into the page at the bottom. So it's clockwise. If you look at this from the end here, this is clockwise. And that's the direction here that's shown. The loop's induced current and EMF are clockwise. After a while, of course, this only works for a very short time. After a while, and we'll talk about this when we talk about RLL circuits, the current will be steady, and the minute the current's steady, the induced EMF and the current drop to zero. So we have had this for a long time, and it's had plenty of time to reach its steady state. So after a long time, the switch, which was closed, is now open. The current, which was flowing from the positive battery terminal through the coil, decreases. The right-hand rule for the electromagnets, we wrap the fingers around the core of the electromagnet in the direction of the current. In other words, your fingers go over the top of the coil, like the top of the electromagnet, like this. Okay, your thumb points to the left in the direction of the magnetic field, and because we've cut this now, the magnetic field and the current are both decreasing. The magnetic field is pointing to the left, and the field inside the loop here is decreasing as the wire's current decreases. The loop will develop a magnetic field to oppose this decrease, so the loop's magnetic field points to the left. The right-hand rule, the thumb points to the left, the fingers curl into the page at the top of the loop. So if you look at this from the side, from this side here, the current is going in this direction with this little arrow here. And if you looked at it from this side, from the electromagnet side, that would be counterclockwise. The induced current and the EMF are into the page at the top of the loop or otherwise counterclockwise. After a while, more later on how long we talk about our RLL circuit, the current drops to zero and the induced EMF and current also drop to zero. Okay, so now this one's a tricky one. Now we have a north pole of a magnet approaching a loop. And of course, the magnet and the loop are both in the same plane. So we're going to determine the direction of the induced EMF. The B field is pointing to the right and it's increasing. But the loop does not enclose any of the magnet's B field, and this situation is not changing. So no current or EMF is induced in the loop. I told you it was a tricky question. Now this one's a little hard to see. We have a loop, the magnetic field is going off to the left here, and this loop is rotating. The left side is coming toward us, and the right side is pushing away from us. The magnetic field points from right to left. We want to determine the direction of the induced EMF. The B field is pointing to the left, and the field inside the loop is increasing as the loop turns into the field. The loop is enclosing more and more magnetic field lines. Now that's only until this loop is perpendicular to the field. At that point, it'll start decreasing. We're not worrying about that yet. The loop will develop a magnetic field to oppose this increase. So the loose induced field points out of the page and increasingly to the right as it turns. The right-hand rule says the thumb is out of the page, the fingers curl counterclockwise. So the induced EMF and current are counterclockwise. Now as this rotates further, the induced EMF will reverse direction. And this is an AC generator. We'll talk more about that later when we talk about generators. Now we need an example. We're going to talk about induction and energy transfer. So we have a rectangular loop of wire, a width L, has one end and a uniformly external magnetic field that is directed perpendicularly into the plane of the loop. So in other words, that's what these little X's are. The field may be produced by, say, a large electromagnet. The dashed lines in the figure here show the assumed limits of the magnetic field, and we're going to neglect any fringes at the edge. You have to pull this loop to the right at a constant velocity v. How much power do you need for this? Well, magnetic field and conducting loop are in relative motion at speed v, and the flux of the field through the loop is changing with time as this gets pulled out. This causes a flux decrease, otherwise known as a flux change. To pull the loop at a constant velocity v, you must apply a constant force to the loop because a magnetic force of equal magnitude but opposite direction acts on the loop to oppose you. Now, these two forces here cancel out because they're equal and opposite, but this is basically you have to fight this. So the rate of work, that is power, is that then power equals F times V, where F is the magnitude of the force you apply to the loop, and V is how fast you're pulling it out. So to find the current and find the induced EMF, we apply Faraday's law. When we have a length x of the loop still in the magnetic field, the area of the loop in the field is L times x. Then the magnitude of the decreasing flux of the loop is phi b equals BLX. Faraday's law tells that this flux is decreasing, and when it is, an EMF is induced in the loop. We can write the magnitude of this EMF as EMF, and we're going to ignore the sign. We only care about the magnitude. The EMF is ddt of BLX. The only thing that's changing here is x, so we can pull the BL out. So it's BL dx dt, and that's BLV. Okay, Physics 220 student, sorry about that, go here. Physics 122 student here. The induced EMF. To find the current, we first apply Faraday's law. When a length of x of the loop is still in the magnetic field, the area of the loop is just L times x. Then the magnitude of the decreasing flux through the loop is BLX. Faraday's law tells us that with this flux decrease, an EMF is induced in the loop. We want to write the magnitude of this EMF so we're not worrying about the sign. So the EMF is approximately equal to the time rate of change of BLX. The only thing that's changing is x, so it's BL delta x delta t, or BLV. Okay, so here, this is what's actually going on in here. Here's the loop being pulled. Here's the schematic of the circuit here. And this shows the loop as a circuit. The induced EMF is represented here. Now notice it doesn't have a battery, it's just represented as EMF. And the collective resistance of the loop is represented on the right as R. We find the magnitude of the induced current. We apply the equation I equals E over R. That's just a version of Ohm's law. So I equals BLV over R. This induced current flows in the wire and interacts with the magnetic field, producing forces on the wire segment that are in the magnetic field. The two vertical forces cancel out because they're equal and opposite. The vector sum of the horizontal forces indicates that the force that you exert to pull the loop at a constant velocity V is equal and opposite to the force F1. So that's this. So F equals F1, that equals ILB sine 90 degrees, or ILB. We're going to assume that B and L are perpendicular. So then F equals B squared L squared V over R. BL and R are constant. The velocity V will be a constant if the force F is also constant. Okay, so induction. The amount of EMF induced depends on how quickly magnetic field lines are traversed by a wire. Very slow motion produces hardly any EMF at all. Quick motion produces greater EMF. Increasing the number of loops of wire that move in a magnetic field increases the induced EMF in the current of the wire. Pushing a wire into twice as many loops will induce twice as much EMF. Find the rate at which you do work on the loop as you pull it from the magnetic field as power equals F times V. That's B squared L squared V squared over R. The work performed in pulling the loop through the magnetic field manifests as thermal energy in the loop. We were going to replace the loop with a solid conducting plate, and we can repeat the process of pulling the plate out of the magnetic field. And instead of getting this nice current here, we get all these eddy currents. Eddy currents are induced currents caught within the plates, creating thermal energy. These eddy currents are evidence that an electric field has been created by a changing magnetic field. And notice, this electric field does not begin or end on any charges. Remember I told you a long time ago that we're going to encounter an electric field that doesn't begin or end on charges? Here it is. Okay, the eddy currents are useful in magnetic braking and for detecting metals. That's how metal detectors work. And of course, we also want to look at maybe vehicles too. This can be used to detect vehicles as stoplights to turn the stoplight. But eddy currents are wasteful in transformers. They heat up the transformer, which is undesirable. Problem 3, Physics 222, stay here. If you're 122, skip one slide ahead to slide 42. Okay, so we have a wire sliding on conducting bars. This is the same thing, physically speaking, as the previous example of pulling a loop out of a magnetic field. The flux is changing, and EMF and a current are then induced. Assume the magnetic field is perpendicular to the velocity, so phi b equals BLX. So BL is the area in here. Okay, so the EMF is ddt of BLX, and the only thing that's going to change is x. So it's BL dx dt, or BLV. This induced EMF is called the motational EMF due to this motion. You can see the word motion in there. So I equals BLV over R. And F equals Fm, that is ILB sine 90 degrees, or ILB. So the power is F times V, that's B squared L squared V squared over R. If you are a Physics 222 student, please, you are finished with this lecture, okay? And you can go on to part 2. If you're a Physics 122 student, bear with me, you've got one more slide. Okay, so here's an example, sliding of a wire or a bar, sliding on conducting bars. This is the same thing, physically speaking, as the previous example, pulling a loop out of a magnetic field. The flux is changing and an EMF and a current are induced. Assume the magnetic field is perpendicular to the velocity. Phi B, which is the flux, is BLX, and of course LX is just the area that's here inside this loop here. The EMF is approximately equal to the time rate of change of BLX. The only thing that's changing here is the X. So it's BL delta X delta T, and that is BLV. This induced EMF is called the motational EMF because it's due to the motion of something. So I equals BLV over R. F of B equal Fm, that's a magnetic force, is ILB sine 90 degrees, or ILB. So the power is F times V, that's B squared L squared V squared over R. Okay, that is the end of part 1. Please go to part 2. So you need lecture 7-1B, induced EMF part 2. Thank you.